In this series of videos, we're going to review Bohr-Rutherford diagrams, Lewis dot diagrams, and also the formation of ions. So this video will use this slide deck as well as this handout over here. Nope, not that one there. The handout over here in order to learn those concepts. It's actually a series of videos that will be broken up into a few separate videos going through each section. So let's go ahead and start section number 1, which is essentially on Bohr-Rutherford diagrams and reviewing the subatomic particles. So when we talk about atoms, we can represent them using a variety of different ways. And one way is using a Bohr-Rutherford diagram. The Bohr-Rutherford diagram is a way of representing an atom and all of its subatomic particles. So all of its electrons, all of its protons, and all of its neutrons. So everything is kind of shown there. So for example, in this picture here, you can see we have the Bohr-Rutherford diagram for carbon. And carbon, if you look on the periodic table, it has, here's carbon, it's 12.01 mass, and then 6 atomic number. So this atomic number means there's 6 protons and 6 electrons. And then if you do 12 minus 6, that's going to be 6 neutrons there. Now, we've already seen how to do Bohr-Rutherford diagrams in our extensive reviews, but again, this is just an example over here where we have our 6 protons in a nucleus, 6 neutrons in a nucleus right there, and then we show all the electrons. 2 electrons in the first shell, and then 4 on the last shell. Typically, the rule is 2, 8, 8. It means you can fit 2 electrons in the first shell, 8 on the second, 8 on the third. In reality, you can actually fit 18 on the third shell, but we simplify that in grade 11. So in grade 11 and 10, we often say it's 2, 8, 8, and 18 on the fourth, but in reality, 18 starts on the third. So just remember that for grade 12. It'll be a little bit different when you get there because you use a different model of the atom to talk about it. But here we're talking about the Bohr-Rutherford diagram model. And so let's briefly go into the subatomic particles and see their characteristics. So there are 3 subatomic particles, sub meaning smaller than the atom, the protons, electrons, and neutrons. Remember that protons have a charge of +1, electrons have a charge of, and you can fill this out as we go because you might already know most of it, -1, and you can maybe get this one before me, neutrons would have a charge of, that's right, 0. And we often represent protons by P+, electrons by E-, and then neutrons by that N0 or N0 on top there to show that there's no charge. And then the mass of these subatomic particles varies, but all the mass of atoms come from their protons and neutrons, so they have an atomic mass unit of 1. So if you were dealing with one individual proton, we don't use grams because it would be so small, so we use the atomic mass unit instead. And electrons are so light, we just say they have a mass of 0 when it comes to atomic mass units. Their mass is negligible, so light they almost don't count when it comes to the mass of the atom. And in fact, that's true. All the mass of the atom comes from the nucleus. For example, carbon, 6 neutrons and 6 protons, a mass of about 12. We'll talk about why there's a decimal number, a fraction number there later on for the mass, but that's the general idea for now. The location also differs for these. So protons and neutrons are found in the nucleus, whereas electrons are found in the shells, or orbits, or energy levels. There's a variety of terms you can use for that. Another very important part to understand is that the number of protons determines the identity of the element that you're talking about, that you're dealing with. It's the number of protons that actually determines what your atomic number is. And in general, what element you're talking about. So an element that has 6 protons has to be carbon, no matter what, because carbon will never, because protons will never change when it comes to a specific element. Protons are not gained and they're not lost during a chemical reaction. Electrons, like I said, they have a negligible mass, which basically means it doesn't really count in terms of the mass. It's so light. Generally, in a neutral atom where there's no charge overall, the number of electrons and protons will be the same. But atoms can gain or lose electrons when they react. And so when atoms gain or lose electrons, they become charged. And when an atom becomes charged, we give it a special name called an ion. So when electrons are gained or lost, ions are formed. An ion is basically just a charged atom, and the reason it's charged because now you no longer have equal number of electrons and protons to balance each other out. If you lose electrons, you have more protons now, and so you're positive. If you gain electrons, you have more electrons now, and so you're negative. And we'll talk about that in more detail in the next part of the lesson. But generally, atoms will lose electrons or gain electrons to become more stable, to get a full octet, just like what would it be? What are those elements called? The noble gases. That's right. And then, as I mentioned earlier, neutrons are neutral. They they can change. So different. So for a certain element, let's say carbon, for example, carbon. There's some carbons out there that have a mass of 12. Some carbons out there that have a mass of 13. Some carbons out there in nature that have a mass of 14. Um, since these are all carbons, uh, they all have 6 protons. And assuming they're neutral, they all have 6 electrons. The mass doesn't have anything to do with the electrons. Um, so why would they have different masses? Well, that's because they have different number of neutrons. So the one with fewer neutrons is the lighter one. So carbon 12 probably has fewer neutrons. Carbon 13 has one more, and carbon 14 has two more than carbon 12. So we call that isotopes. They're basically atoms that have the same number of protons, but they differ in terms of their mass because they have different number of neutrons. So it's kind of like saying there's different versions of carbon out there. Carbon that's light, carbon that's heavy, and carbon that's in between. So they would all have 6 protons each, but the number of neutrons would differ. So for example, this would have 6 neutrons to add up to 12. This would have 7 neutrons to add up to 13, and this would have 8 neutrons to add up to 14 when you have the 6 protons in there. And so those are called isotopes, and we have a whole lesson on that coming up shortly. Um, a few other terms you should know are the valence shell and valence electrons. Valence shell is the outermost shell of any atom, and any electron found in that valence shell, those are called valence electrons, the outermost electrons, and they are the ones that participate in chemical reactions. They're the ones that form those bonds. So I want to go into a bit of detail of the energy levels of where electrons are found, those little shells or orbits. The shells or orbits of Bohr-Rutherford diagrams or of atoms, they differ in the amount of energy that they have. So if the electrons are really close to the nucleus, there's less energy in that electron orbit and then that electron because they're held down tightly to the nucleus. So if they're really close to the nucleus, there's not a lot of energy there because the nucleus is positive and holds those electrons down, and there's not much they can do. But the farther away an electron is from the nucleus, the more energy it has. Because it's not as held as tightly to the nucleus since it's farther away from that positive charge. So the cool thing is electrons can actually jump from a lower energy level to a higher energy level. So for example, the electron here jumps to here if you give it energy. So if you shine some high energy light onto it, or you heat it up a certain way through a fire, for example, you're going to give the electron some energy and it'll jump up to a higher energy level. So electrons can jump up in energy levels when they receive light. And I should say absorb light energy. The energy in the form of light, we give it the term photons. Not protons, but a photon of light. It's like a packet of light energy. Now, the electron, once it jumps up in energy level, it won't stay there forever. Eventually, it goes back down. And when it goes back down, it has to release the energy it absorbed. It releases not all of it, or actually it releases all of it, yes, but it's not all in the form of light. Some of it could be lost as heat as well. So it'll release some energy as light, and then some energy sort of released as heat. So when an electron drops down the energy level, it releases a photon, or we can say emits, like to give off, to send out a photon of light and also some heat generally. So when the electron is kind of found in its low energy state, we call that the stable low energy state. We call that the ground state. That's typically after the release of energy. So when you come back down to having kind of low energy levels, we call that ground state. But when you absorb energy and the electron jumps up here, the electron is going to be in what's called its excited state, a higher energy level. So it's after the absorption of energy. And so let's go quickly discuss what this picture here is. So what you'll notice is this little band over here. And this is basically if you put an element through, you give the element energy, its electrons will absorb light and they'll jump up to a higher energy level. So for example, I might have an electron over here, it absorbs light, and then it jumps up to here. When it jumps back down, it's going to release the energy it absorbed in the form of heat, but also light. And so these little bars that you see over here, these are the types of light that electrons released when they went back down to their ground state from their excited state. And so the cool thing is the elements, different elements have different sort of patterns of light that are released when they go back from their excited state to their ground state. And you can tell what elements you have in a mixture, in a star or something, by studying this little spectrum over here. So essentially what we have here is we have an absorption or an emission spectrum. This is called an emission spectrum. Emission spectrum. It's basically just a picture that shows you what colors of light are released by the electrons of an atom when they come back down to their ground state after you shine some light or heat them up in some way, shape, or form. Let's go take a quick look at that in our little slide deck over here. So let's go here. So as you can see, we have an electron in its ground state, photon hits it, it jumps up to a higher excited energy state. When it comes back down, it's going to release energy as light and heat, and this is the sort of the energy level of the light that was released. Different colors of light essentially have different amounts of energy in them. Usually you have higher energy sort of in this end over here, the violet end, and then in the red end you have lower amounts of energy overall. Here you can see that generally when you're talking about light, there's a reading about this that you'll do. The colors like red have low energy, and the colors like violet, like I said, have higher energy. And it all has to do with the with what's called the wavelengths. So notice the red is a large wave, and because it's a large wave, we say it has low frequency. Low frequency. What that means is it doesn't repeat as often as something that has smaller waves, because this repeats more and 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 more. This is higher frequency. So if something has long waves and low frequency, it's usually lower in energy. If something has short waves and high frequency, there's more energy, like the purple light. And so this here is a cool demonstration that illustrates the idea of electrons being released or energy being released when electrons jump back down from a higher energy state. This is chlorophyll from plants. So what you do is you take some spinach leaves, you crush them up, and you put a solution in there to take out the chlorophyll. And then what you can do is you can shine some UV light onto the chlorophyll solution that you made. And what will happen is the electrons will absorb the UV light, and then when they jump back down, they'll release the light as a red color over here. So they absorb high energy light and they release the light as a red color. It's a lower energy light, and then the rest of the energy is released as some form of heat. But this is a really cool, easy demo that you can do. We often call it plant blood. So when you go back to the classroom, you can ask your teacher to try that demo out if you're very interested in trying it out. And here's just another picture of the ground state versus the excited state. So you can see these electrons here are very close to the nucleus, so they're in their ground state. Then you give them a photon, they absorb it, and they jump up farther away from the nucleus. They're in their excited state. And then once they release the light, they jump back down to their ground state. And this light might be a lower energy than what was absorbed, but that's okay because there was also some heat released. Total of the heat and light is basically going to amount to the total of the light that was absorbed initially, because you have to get back down to the exact same spot you were at before.